In this video, we want to look at the dynamics or the relationship between a plane and a plane. Firstly, they can be known to be what is called incident planes. Next, they can be what is called parallel planes. And thirdly, non-parallel planes. To be incident planes, the two planes must first and foremost be parallel to each other. How would you know if two planes are parallel to each other? The moment the two normal vectors are parallel to each other, then the two planes will surely be parallel to each other. In the case of incident planes, apart from being parallel, you find that in this case, if one plane can be reduced to the equation of the other plane, then these two planes are like one and the same plane, or you can think of them as just two planes where one is overlaying the other, and we call them incident planes. Secondly, if they are parallel and distinct, like in this case, if they are parallel, how do we know if they are parallel? Again, when these two vectors are parallel to each other. When two planes are parallel and distinct, like in this case, then naturally we want to look at the distance between these two planes. If you look at these two planes like two straight lines, plane 1 and plane 2, we want to learn how we can actually find the distance between two parallel planes. To find the distance between two parallel planes, a very important first step is for you to reduce one equation such that it has the same normal vector as the other one. So for this case, I'm going to rewrite equation 1 as r dot 1, 2, 3. Okay, this is the first important step. I have reduced equation 1 so that now it shares the same normal vector as equation 2. And now we are ready to try to find the distance between the two planes. If you see these two planes as like two straight lines, and then you have a point A on the first plane and a point B on the second plane, it's always possible to have a point found on the first plane and a point found on the second plane. So then this vector will become A minus B. Then for the common normal vectors, like in this case, they have a common normal vector 1, 2, 3. I can write this common vector or draw this common vector over here, or even over here. Because this normal vector is just a free vector, I am at liberty to draw them here, or even here. So in this case, I've drawn my normal vector n as here. If you draw the normal vector n here, then you will realize that to find the distance between the two planes is as good as finding the length or projection of this vector onto this. And we have learned in earlier videos that it is just this vector dot with n cap. I've written n cap as n over modulus of n. Computationally, what is going to happen is from this first line, I can actually expand it as a dot n minus b dot n. If A is a point on the first plane, then A dot n will be equals to 2. If B is a point on the second plane, then B dot n will be equals to this number. So what I do is I put this number as 2 and this as minus 7 in this example. And there we are able to find the distance between the two planes in this very easy manner. And this calculation can be summarized as a very nice formula d1 minus d2 over the modulus of n. What is d1? d1 is simply the number on the right of the first equation, and d2 is actually a number on the right of the second equation. So by taking the difference of the two d's and divided by the common normal vectors, it is important that this is the n is a common, it must be the same common normal, right? Common normal vectors. Right, if the n is a common normal vectors, then this formula works. And thirdly, we now want to look at the case where the two planes are non-parallel. When two planes are non-parallel, like this diagram, if these two planes are non-parallel, then these two planes will surely meet along a line. Okay, if two planes are non-parallel, they will surely meet along a line. So can you imagine if these are two planes? If these are two planes, they are non-parallel. Two planes which are non-parallel, in this case, right, in this example, if these two planes are non-parallel, they will meet along the core of this foolscap paper. You can see, right? This is like the intersecting line between the two planes. I can see them as like this, or I can see the two planes as like that. You can see. And then this is actually the intersecting line between the two planes. So naturally, we will be interested to find this intersecting line, whether you draw this way or draw it like this. To find the intersecting line between two planes, there are actually two approaches. I shall discuss the first one, and then later on the second one. For the first approach, looking at this diagram, I can actually capitalize on the fact that if I were to cross product these two vectors, like this, if I cross product these two vectors, I can immediately get a vector that is, in this case, if I cross product, I get 1, 2, 3. And this vector 1, 2, 3 will be actually parallel to the intended line over here. 1, 2, 3. What's happening here is, what I'm saying is, if you have two planes, right? If I take the normal of the first plane, cross product with the normal of the second plane, I'll get vector that's like this. Once again, you take the normal of the first plane, cross product with the normal of the second plane, you get vector that's like this. And this immediately gives me a vector 1, 2, 3 that's parallel to the intersecting line. Now, in writing down the equation of a line, we need two things, right? First, we need the directional vector of a line. We also need another thing, and that is we need at least one point on the line. And how do we go about finding that just one point on the line? There are many possible points, but we just need one. And how do you get at least one point on the line? We can start off by thinking that this point on the line is A, B, 0. You can arbitrarily give the last element a 0 value. So if this point indeed is on this line, if this point is indeed on this line, this point is also in pi 1, is also in pi 2. That means this point must satisfy the equation of the first plane, and it also must satisfy the equation of the second plane. So what does it mean? It therefore means that if I have to plug in this into here, I get one equation which is A minus 2B equals to 12. And then I plug the second equation, I will get 3B equals to 21. If now you solve for A and B, believe me, if you solve for A and B, your A will turn out to be how much? If you solve for A and B, your A will turn out to be, B will be 7 and A will be 28. If you solve them simultaneously. Right? So we can then affirm that this point truly is on this green line by verifying that this point is on the first plane and this point is also on the second plane. So I've given you a method to find a point on the intersecting line. Of course, if you're very clever, you could potentially just spot on this point without any calculation. But for most of us, we will probably take this approach of giving the last entry 0 and finding the other two numbers so that together they can satisfy both planes. As a word of caution, it could be that such a point does not lie on a green line like this one. It could be, let me say, if you try 0 as a third entry, it doesn't work, you do something strange, then all you need to do is maybe start off with 0 for the first entry and then B and C, and then find B and C through the same approach. But in any case, in my example, things works very well. What I have here is a point on the intended line and the directional vector. So therefore, this equation on the line will look R equals to the first vector, which is 28, 7, 0 plus lambda of 1, 2, 3. And there we are, the equation of the intersecting line between the two planes. There is yet another approach to finding the intersecting line between two planes. How do you go about doing it in a second way? So in the second way, it goes this way, it goes like this. You rewrite this equation as Cartesian, and then you just give put z as lambda. So then you move this to the right hand side, and then you now have an equation of x, y, and y. This equation 1, this equation 2, having replaced the z as lambda. You now want to solve for x and y in terms of lambda. If you solve them, you find that your x and your y will turn out to be, your x will turn out to be 28 plus lambda over 3. Your y turned out to be 7 plus 2/3 lambda, and this is just lambda. Right, maybe let me write bigger a bit because earlier on I was just afraid that it does not get reading the screen. Let me write again. If you solve them, you get x, y, z equals to 28 plus lambda over 3, and then y is 7 plus 2 lambda over 3, and this is lambda. So this one gives you actually an equation of a line which looks like this: 28, 7, 0 plus lambda of 1/3, 2/3, and 1. So this offers you another way to find the equation of the intersecting line. For the case of non-parallel planes, apart from finding the intersecting line, we are also interested in another thing. Let me draw these two planes as two edges, plane 1 and plane 2. In this diagram, if I ask you where is the intersecting line, actually the intersecting line is into the port. Let me mark it as like this. It's actually into the port. Okay. Now, if you draw it this way, then you can see that actually we will be interested to find the angle between the two planes, which is here. How can we go about finding the angle between two planes? Even if I have not told you about it, you can potentially guess that the angle between the two planes could have been easily found by cos theta equals to n1 dot n2. Why should this be so? To understand why, if you look at this diagram, for the plane pi 1, maybe its normal vector is like this n1. For the plane pi 2, the normal vector is maybe like this, right? And then using simple geometrical reasoning, you can immediately spot on that if this angle is theta, then this angle is also theta. So from what you know, to find angle between two vectors, you have this nice formula to tap on. But to safeguard the possibility that instead of going upwards for M1, instead of going upwards, if M1 were to point downwards, then the angle sandwiched by N1 and N2 is no longer the acute angle theta. And in this scenario, perhaps you therefore want to put a modulus to take care of the possibility that M1 could point in the other direction. So by taking the modulus on the numerator, you are guaranteed to find the intended acute angle between two planes. So this brings us to the end of our discussion on the dynamics or the relationship between two planes. Let me just do a touch up. I realize that this is not really visible. Let me read for you. There's actually R equals to 2870 plus lambda 123, which is the equation of this line. Alright, with this we come to the end of our video presentation on two planes.